So welcome to part 28.3 of operational amplifier circuits. And in the last video, if you recall, we thought about what operational amplifiers are in kind of an abstract mathematical sense and kind of how they work and how we can calculate some numbers. But in this lesson, we're going to take a look at what these are actually used for in everyday life. And they're used in a lot of things, from everything from computers to thermostats and to a whole bunch of electronics. And basically they serve as computational devices in a physical sense. But we're going to take a look at a special case of a thermostat today. And you find thermostats in homes, and also we're going to take a look at kind of the electronics of a toasted sandwich machine. And they might seem a bit unrelated, but I promise these will all come into view very shortly. So since it's been a long time since the last video, let's take a look at a refresh of what an operational amplifier looks like. And here it is right now. It's kind of a black box. You can't really see much of what's going on, but if we recall, it's just a whole bunch of transistors, resistors, all kind of in a single compact unit. And we don't really need to know how it works very intricately. We just have to know how it works practically, in a pragmatic sense. So, now that I've jogged your memory, hopefully, let's take a look at what the first kind of fundamental use of an op-amp is, and that's as a comparator. And a comparator is just as the name seems. So what I'm going to do is I'm going to draw an op-amp, and if you remember, there's an inverting negative input and a non-inverting positive input. And there's a negative power supply, and there's a positive power supply. And also there would be an output. Correct? Fantastic. Okay. And basically, if we recall, the formula we're going to use here, well, I don't like to talk about formulas too much in physics because I think it detracts from the kind of core concepts, but basically, the voltage of an output is equal to, as I explained it before, what this basically does is it takes these two inputs, the non-inverting and the inverting, and it kind of mashes them together, except it multiplies the inverting one by -1. So it just takes a summation of these two voltages. So if this was -2 and this was 3, it multiplies -2 by -1, making it 2 volts in here, and then it takes the 3 volts from here. It kind of multiplies them like a little computer, and then it outputs 5 times the gain, which we call A naught. So that's just a bit of memory jogging. So what it does is it takes the A naught of the positive input minus the input of the negative value. And if you can see this is actually a difference. We recognize in math all the time. The difference between 5 and 3 is 2. It's 5 minus 3 equals 2, right? So this is one of the fundamental uses of a comparator. We can take the difference between two voltages. And you still might be thinking, well, how's that going to help me in life, right? How does this have any practical application? And let's take the example of a thermostat. So a thermostat you can set to kind of control the temperature in a room. And I'm going to take a bit of a more simplistic view of this, but you'll see how this works soon. So what I'm going to do is I'm going to put a circuit here of two LEDs. One facing this way and one facing this way. And remember that LEDs are kind of like diodes? They are the light emitting diodes, which means they only let current pass in the direction where the arrow is pointing. So let's say this is connected to some circuit and it's grounded here. And I'm going to connect this to another circuit here. So let's say over here I have 4 resistors, right? I have resistor 1, and I like to put numbers on these so that we can kind of see how they work in a very real sense. So let's say that these two are 5 ohms each. Let's say that we have another one here of 5 ohms. And then we're going to have a special one, which I'm going to draw another color. Let's draw it in pink. So this one here is my special one, and I'm going to call this T, kind of T squiggles, ohms. And these can be connected to the same power supply, arbitrary power supply. So let's say that these are connected to a 10 volt power supply. we go. Fantastic. So let's say the power supply running through this is 10 volts. And if you remember, think about this logically, if you think about Ohm's laws, the potential difference from this point to this point has to be the same as the potential difference from this point to this point, and they both have to be equal to 10 volts. And the reason for that is when the electrons split up here and later rejoin down here, if we just think about this kind of big square in isolation, they rejoin down here, the voltage of these electrons are the same at this point, and when they rejoin, the voltage of the electrons have to be the same when they rejoin as well, because when they become one unified stream again, that stream has to, all the electrons in that stream must have the same property, because electrons are fundamental particles and therefore are all exactly identical. So 10 volts expanded between these two resistors here, and 10 volts are expanded between these two resistors here. And if you remember, to calculate, what we're interested in is the connection. So this one here is connected to the non-inverting input. Sorry, I should have drawn this as a kind of a bridge jumpy thing, which means that this does not actually connect at this point. So let me just fix that. So over here, it does not actually connect. So we'll take a look at that. See, there we go. Fixing that. So it doesn't actually connect at that point. And this one here, we're looking at. So basically, what this in this example, what this comparator is doing is it's taking the difference between voltage at this point and the voltage at that point. And if we kind of think about this, to figure out how much voltage is expended in a resistor, the equation is V equals IR. And what we know is that the voltage going through this resistor is the same as the voltage going through this resistor, correct? Sorry, not the same current goes through both these resistors. Therefore, the voltage expended is in direct proportion to the ratio between the resistances. So we can say at point, let's call this P, the voltage at P is equal to the resistance of the first resistor up here, 5, divided by the ratio of the resistance of a whole circuit, which is 5 plus T. And here's where it gets really cool. T is a thermistor, which is a resistor which changes in accordance to temperature. So the resistance of the circuit can actually respond to external stimuli, in this case temperature. And when this responds, we can actually change the output. And when you change the output, you can change the effect that this has on the real world. So let's take a look at this, right? So let's say on a cold day, the thermistor has a high resistance because of the fact that, if you think about it, you can think of a thermistor like a pool, and the atoms of that make up that thermistor are like people in that pool. And on a cold day, if it's cold, they don't have much energy, so they all kind of just stand around, kind of vibrating amongst the spots. And when an electron wants to move through that pool, it's hard because everyone's kind of serving as roadblocks, and that therefore has high resistance. Whereas on a hot day, everyone has energy and everyone can move around freely. And when everyone can move around freely, electrons can also move freely through it. So let's take a first case, okay? So let's call this case 1. Case 1. It's cold, right? So let's say it's 5 degrees Celsius. And so in this case, the resistance will be high. Let's say the resistance is 10 ohms. So in case 1, the voltage therefore is 5 over 5 plus 10, which is 5 over 15, which gives us 1/3 of the total voltage. So sorry, I should have multiplied this by the voltage, which in this case is 10 volts because it's a 10 volt circuit. So voltage is 10 volts, right? Basically, the voltage at this point on a cold day would be 1/3. So let's just write that down. It would be 1/3 of 10 volts, which is 3 1/3 volts. And obviously the voltage at this point would be unaffected because these two resistors are constant. And that would be 5 volts. So, and this is a non-inverting, and this is inverting. So we take the 5 volts, multiply by -1, giving -5 volts, and mash it up with a 3 volts. Therefore, the total the total input into this operational amplifier at this point in time when it's 5-degree day would be negative 1 1/3 volts, and therefore the output of that would just be negative 1 1/3 times whatever A naught is. Let's say in this case it's a number which will always saturate. Let's say that this would be 10 to the power of 5, right? So on this cold day, it saturates at 10 volts, and therefore this is just this becomes negative 10, right? Because it's a negative number. And let's say the negative direction of the circuit is counterclockwise, because remember, positive, negative volts, current is always a negative charge. When we say the potential difference is negative, we say in relation to ground, it's less positive than ground, and therefore it's really just the direction current is flowing. So on a cold day, current flows this direction only, like that. It flows in this direction only, like that. And if you can see, what happens at this light emitting diode, it's going the wrong way, so this one will not light up, and this one will light up. So let's call this light red. Okay, we'll call this light red. And that, you can see what happens on a cold day. On a cold day, only the bottom resistor would light up. This one lights up on a cold day. Now let's consider the case of a hot day, right? So as I said, when it gets hot, the resistance kind of drops a bit. And let's say on the hot day that T becomes, so I just have to make some space here. Sorry about that. So let's consider case 2 now. So let's say on a hot day, we've now moved to the desert, and I'll do this one in orange. Case 2. On the hot day, let's say the resistance is 2 volts, right? Sorry, not 2 volts. Let's say it's 2 ohms. So if it's at 2 ohms, when it's at 25 degrees, let's think about what a ratio is. So the ratio will be 5 over 5 plus 7, and that's just 5 over 7. And if we want to take that kind of numerically, we can see that 5 over 7 is simply about 0.714. So I just did that on my calculator here, and let's just put that over here. So the potential difference at this point P now is now 5 over 7, which is 0.714. And let's times that by 10, because the voltage of a circuit is 10. So the fraction, was 0.7 approximately, and now so the voltage at point P is 7 volts. So therefore the total voltage going into this operational amplifier would be, let's just approximate to 7 minus 5, and that puts it at positive 2 volts. So with a positive input like this, the output's also going to be positive. And what's the difference? Basically, that just defines the direction of the current to be opposite what it was when the output was negative. So when we said that the positive one kind of went from right to left, but the negative one went from right to left, this positive one must therefore go from left to right, in this way. And if we send current this way, this diode no longer lights up, and this diode lights up, and it gives us a green light. In this sense. So look at this. So that's quite remarkable if you think about it. So let's say in case 2, the voltage. So in the case 1, the voltage is only 1/3 of the voltage of a whole circuit. In this case, it's 5/7. And in this case, we get in case 2, we get the green light, and in case 1, we get the red light. So I'm sure many of us have used things like ovens or toaster sandwich machines. When it's cold and not at the correct temperature, the red light might go on to say, hey, we haven't got to the right temperature yet, because the ratio between these isn't beyond our predetermined value yet. But when the temperature raises enough and the resistance of this changes to be low enough, the voltage of this will overcome the voltage of the inverting input. So the voltage of a non-inverting input will become greater than the voltage of the inverting input in absolute terms. and therefore the whole direction of the current will swap round, and a different light will turn on. The green light will turn on and say, look, your sandwich or your food or your room is at the temperature you set. And what's more interesting is often, that temperature is not always the same. For example, in an oven, we don't always want to cook everything at 180 degrees. Sometimes we want to cook things at 220 degrees. So this one will often be a variable resistor, so that we can determine what the threshold has to be for this resistor here in order for it to overcome the limit. So we can change the limit. We can make the limit, that you have to have more than 2 volts. We could have it, you have to have more than 4 volts. And you can see this is kind of like a very primitive comparative statement. It's like saying, here we go. So, we can set, I'm just going to get rid of this for a second. So we can say, we can set this. So here we go. So we can say, we can set this value here. So if we call this value Q, right? We can say if P is greater than Q, then start the red light, or else, which is where Q is greater than P, will start the green light. And you see, we've done this kind of computation using an operational amplifier, and all we had to do was compare these two values to see which one was greater than the other one. And because the gain is infinite, theoretically infinite, we don't need to worry about anything. These are as long as it's even slightly greater. So we can work with very precise values and say, if a voltage is 0.001 volts greater, because the gain is 10 to the power 5, it'll saturate anyway, and it'll just make the swap over. So that's the first use, and you can see it's quite a cool use actually, that this operational amplifier can serve as a comparator. So now we have to talk about feedback. So let's take a look at that. I just need to clear some space here, excuse me. And the ability to make a kind of judgment call like that in a physical sense using electronic components is extremely useful, and that's why op amps, you can use it. If you think about it, any kind of sensor that can change resistance or voltage in any way, like a light dependent resistor, or there are resistors that change based on how much tension is being applied. Those can produce an output which we can actually see, and this is how you can see how this can be used in sensors of all different kinds. But anyway, now we need to talk about feedback. And what is feedback? So feedback is basically taking what we've produced and putting it back as an input. So look at this. So I'm going to simplify my diagram. So this is the voltage coming in, right? And it goes into the operational amplifier, and that produces an output. And what we are able to do is takes a fraction of this output, and let's call that fraction beta, and put it back into the input. And you'd think, why do we even want to do this? Because what we're doing is we're actually increasing the voltage. So this is kind of a, and we can actually, you might be saying, hey, we have two inputs here, right? Yeah, so we can actually put this output back into either of those inputs, either the inverting or the non-inverting, and it would both be considered feedback. So this is what feedback is in general, and feedback is kind of used as a control or to kind of modify the function of this operational amplifier. And basically, so let's kind of express this kind of algebraically. So we say the total voltage out. That's a bit of a weird concept. So the electrons go in, and then different electrons come and kind of magnify that voltage, comes back and it magnifies the input, so that this gets magnified even more. And you don't really need to know the full mathematics, but what we kind of figure out to be is the voltage out is equal to the gain, obviously, times the voltage in, plus the fraction of the feedback of the output which is putting back times voltage out. And this is a bit of a weird equation because voltage out appears twice, but we can solve it algebraically, And you can do this if you want, but just to save time, I'm just going to go straight to the answer. It's not a very difficult equation, but the voltage out, ratio of voltage out to the voltage in is equal to the gain of an operational amplifier over 1 minus the gain times the feedback fraction. And we can control the feedback fraction using resistors, which we'll see very soon. And, this is kind of what I like to call the effective gain. So, the effective gain. So, this might be a little bit confusing, but think about it like this. If I put 5 volts in, and this operational amplifier has a physical characteristic of multiplying by 10, and let's just say the power supply is infinite for our argument. The physical, if I didn't have this feedback loop, and I put this as a 10 times multiplier on this operational amplifier, my output would be 50 volts. But let's say I then use to the same input, but I introduce this feedback loop, and I say this feedback fraction to be okay. So we want to increase this. So the feedback fraction, let's say it's 1/3, right? I put 5 volts in, and then I get the physical gain A0, which is 10, over 1 minus 10 1/3, which is actually just is 3.3. So in that case, what this would equal to would be equal to 10 over negative 2.3, which is approximately equal to -5. So what I've actually done is I've actually made the effective gain -5. And we use two types of feedback. You can either have kind of positive feedback, you can have negative feedback. Negative feedback reduces the gain you have, and positive feedback increases the gain you have. And it's just a way of kind of controlling the system. So you can see that the effective gain differs from a physical gain in this sense. And why do we want to do this? Well, there are a few kind of benefits, which I think are just most easily probably memorized. It increases the bandwidth, which, if you remember, is the range of frequencies for which the gain is the same. It decreases the distortion of the output, and it gives the system greater stability. So, this is kind of the kind of reasons why we might use feedback, just in a sense of the benefits without thinking about changing the gain itself. But we kind of need to know now two specific instances of feedback and kind of how to draw them, and also how to calculate the effective amplification in those situations. So let's talk about first the non-inverting output. Sorry if I wasn't too clear on that, but hopefully I just wanted to illustrate the point that you can change the effective feedback, the effective gain of an operational amplifier by using a feedback system, and that's really all I wanted to illustrate from that last diagram. So let's talk about first the non-inverting. There's two types. There's non-inverting and inverting. So there's non-inverting and inverting amplifier. Alright, so let's talk about the non-inverting amplifier. So I'm going to draw it. It's quite simple, and the reason it's called non-inverting is because the only voltage input in this case comes from the the non-inverting side. So here we go. So that's the inverting. You have to kind of understand that in both these circuits, the feedback always goes into the inverting side. So this is the voltage in. This here is the output. And here we'll have ground. And here we'll have two resistors labeled RF and labeled RI. and I'll draw some lines here to show that this voltage here between here is a V out, and this voltage here is V in. You might wonder, why am I drawing lines? Well, remember, voltage is always comparative, so we always compare to something. So I compare to the ground, which I call 0 volts, or the earth, and therefore it gives me the voltage in and the voltage out. And basically a fraction of this goes back towards a fraction of the output. So the electrons come in through here, go through here, get outputted, a fraction of them come back around, come back and go through the circuit again, and change the value of the inverting input. So this kind of changes what the effective gain is. And the overall voltage gain of this amplifier is given by this equation here, which you can see here. 1 plus RF over RI. So remember, in any kind of resistor circuit that looks like this, the potential difference at this point would be the same as the input into the inverting. So to see this changes depending on the ratio between RF and RI, and this is how you derive the effective amplification of a non-inverting system like this. And for this case, we do not need to know how this is derived. We just have to remember this is how it's drawn, kind of have a basic grasp of how it works. So if you can see here, the A0, the value of its physical amplifier, the physical amplification value of this op-amp is not incorporated in the system, and we can change its gain just by changing what values of RF and RI. So if RF was 1 and RI was 1, the whole gain of the system would be only 2, and that's a lot different from 10 to the power 5, if we recall from before. So basically, this one we don't have to know that well, and I've saved the harder one for the second, which is the inverting input. So let's take a look at the inverting input. And this one we actually have to know how to derive a formula from it. And it's called the inverting input. Remember, but in both our circuits, the feedback always goes into the inverting input. But in the inverting circuit, which is the one we're doing now, the voltage in also goes in. So let's take a look at that. So the non-inverting input goes straight to ground, which is quite interesting, something that we haven't really seen before. And the non-inverting input actually has kind of two interesting kind of parts to it. So this one is called RI, and let's call this one, it actually attaches to, we have a point here called P, and then there's another resistor here called RF, and this comes down, comes across to here, and then of course we need to see where our inputs and outputs are. So this one here is called V in, and this one here is called V out. So it's a similar idea, and basically all we've done is we're saying that the voltage in comes through the inverting input instead of a non-inverting input here. And you know, we got to think what's the effective gain in this case, and in this case this formula no longer applies. This is only for the non-inverting, right? So for the inverting, the formula is as such. It is V out over V in equals, and this one's quite simple, it's minus RF over RI. So it's a little bit different from the other one. And the thing is, we actually have to know how to derive this in A-level physics. So where does this come from? And it all comes from the supposition, the principle, that P equals, well, basically approximately equals 0, and because of that it's called a virtual Earth, because it serves the same purpose as Earth, being at 0 volts, because that's what we compare it to. And how do we prove that at point P, this point here, there's 0 volts? And you know, it seems a little bit unintuitive at first, and notice that P is at the intersection between where the feedback joins into the inverting input. You have to remember this. So how do we know this? Well, what we know is that the potential difference across this resistor here divided by the resistance of this is the same as the potential difference across this resistor here divided by the resistance of this. And how do we know that? Well, we know that the current going into a resistor is effectively zero, right? So we know that the impedance is infinite, which impedance is a word, it's slightly different to resistance, but it means that basically no current goes into the inverting input. And basically, as a current flows around here, if you think of a current going backwards, it's a little bit hard to conceptualize, but think of an electron going backwards. When it comes to this intersection down here, none of the electrons go right. None of them go into the inverting input because it has infinite impedance. So this is like a wall that exists here, and all the electrons go that way. Therefore, all the current goes through RF. All the current that went through RF would also go through RI, and it's not exactly. A few electrons will escape there, and this is why we call it approximately zero. But for the purpose of the argument, let's assume it's perfect, and all of them go across. So I'm going to need to make more space here. So in that case, we can say, as V equals IR, therefore R is directly proportional to the voltage expended across that resistor. So let's take a look. Therefore, the PD of Ri over the actual resistance of I is equal to the PD of Rf over the actual resistance of Rf, right? Alright, so if we assume at this point here is 0, right? Because it's a virtual earth, right? And it's a little bit difficult to explain why this is an earth. It's kind of like the argument commonly used, which I'm not completely in favor of, but it makes a bit of sense, is that because the gain of this operational amplifier is so high, 10 to the power 5, and that the non-inverting input has a voltage of 0, therefore the inverting input must have a value very close to 0 in order for this to work. So that even if the difference is very little, that there's still a large output coming out from here. And that's kind of argument that because the non-inverting inverting input have to have a small difference, and because the non-inverting is 0, therefore the inverting is approximately 0. So that's a supposition of why P equals 0. So let's continue this derivation of this equation. So the voltage in minus 0, therefore, because that's a PD across Ri, is this voltage minus, so the difference between these 2 points is the voltage in minus 0, right? Because that makes sense. Over Ri is equal to the difference between these 2 points going in the same direction, 0 minus the voltage at this point, which is V out, right? Equals 0 minus V out over Rf. And all we have to do is rearrange it, and we get to here. And it's kind of easy to see why the negatives come in, because the difference between this point here and this point here is positive, whereas the difference between this point here and this point here is negative. So hopefully that's given you a kind of understanding of how this formula is derived. And I know the second half of this video was a bit theoretical, but hopefully it's gone some way towards your understanding, and hopefully you'll be able to not only understand, be able to answer the exam questions, but also understand it enough to kind of know how this works. So thank you for watching this video, and I'm hoping to make many more in the future. And it's a big help to me if you subscribe or like, and also recommend these to your friends. Thank you for watching, and I'll see you next time.